Hello and welcome back to the lecture on applied econometrics. We are in module 2 and we are talking about econometric modeling, and we are talking about different concepts in this lecture, and in this particular lecture we are going to talk a little about regression coefficient. Now, when we talk about regression coefficient, let me first write down the very simple regression equation where we write, say, y is equal to beta 1 plus beta 2 x and say some error component, right. Now, we have explained that a regression equation, you can always write a component which is stochastic and which is not stochastic. Okay. So, this part, the error term, it is the stochastic component, and this term with the variable and coefficient, this is the non-stochastic component. Now, what do we mean by stochastic and non-stochastic component? So, in stochastic component, you always have some randomness. You do not know what is the value of u is, whereas the non-stochastic component is basically the deterministic component. You have some idea, you actually know the value of these coefficients. Okay. So, that is why it is non-stochastic component. So, when you draw a regression line, they are basically the slopes of that line, slopes and intercepts. So, you know the value. So, the moment you know the value, it becomes non-stochastic component, right. Now, what you have to see is that this beta 1, beta 2, these are all true population parameter. So, for a given population, they are constant, and there is no doubt about it being a stochastic component. But when we come to data that you have in a sample and you try to estimate beta 1, beta 2, do we still have non-stochastic component there, and how that actually looks like. So, that is something we are going to see in this lecture. We will see when we actually do a regression table, we normally use, for example, t-test, f-test, and we create confidence interval. Now, all these things, if you want to do, you really cannot do if you have a fixed constant value, right. It has to have a distribution. Now, where from the distribution is coming. So, that is what we are going to see when it how this population parameter beta 1, beta 2 is estimated from sample parameter b1. I will to differentiate, I will say b1 and b2, okay, and I will write y hat instead of y, because I am estimating using my sample observations. So, now I have to get this b1 and b2, and I have to see how they are related with beta 1 and beta 2. So, we will start with b2. In fact, we will focus on the b2 part. So, the coefficient for x. Now, how do we by definition b2 is summation of xi minus x bar into yi minus y bar by xi minus x bar whole square. Okay. Now, what we will do is we will simply replace the y values in terms of the x values. Okay. So, what I will do, so it means summation of xi, or actually what we can do is we can only take the numerator like we have been doing. So, summation of, so the numerator is summation of xi minus x bar into summation of yi minus y bar. Now, my y equation is nothing but this. So, I will replace my y with this. So, essentially this means summation of xi minus x bar, yi is beta 1 plus beta 2 xi plus ui minus beta 1 minus beta 2 x bar minus u bar. So, essentially I did not use another comma, another bracket there. So, if I further calculate it, I will have this beta 1 cancelled, and what I will have is a, let me use a second bracket, beta 2 xi minus x bar and ui minus u bar. So, this is what I will get. Let me close it also. If I further expand it, what I will get is xi or xi into x bar into beta 2 into xi minus x bar plus I will have summation of xi minus x bar into ui minus u bar. Okay. Now, I take beta out. So, what I will have beta 2 into summation of xi minus x bar whole square, and here I will have xi minus x bar into ui minus u bar. Okay. Now, recall the first equation we had, the beta 2, the expression for beta 2 is this. Now, if I replace, I should have given some number 1, let us say this is 2. If I use the equation 1 and equation 2 together, what I will get is beta B2. So, we have to remember we must not confuse B2 and beta 2. So, B2 is equal to beta 2, then I had summation xi minus x bar square, and then I had summation of xi minus x bar ui minus u bar. Okay. And then I have to divide the whole thing with summation of xi minus x bar whole square, which means what I am left with beta 2, and then I have summation of xi minus x bar ui minus u bar by summation of xi minus x bar whole square. Now, this is something very, very interesting, and this is something we need to keep in mind when we are going to do all these regressions and hypothesis testing of the regression coefficients and so on and so forth. So, note it carefully, you have your beta, you have your B2, this is something you need to be very mindful about, and here you have your beta 2. So, beta 2 is a population parameter, okay. This is a population parameter, and you estimate this population parameter using, you never know this population parameter, all you can do is estimate this population parameter as B2, and B2 actually consists this population parameter which is non-stochastic, and whereas this component you have this error term here. The interesting part here is that you have this error term which is basically the random component, and because you have this random component, this is a stochastic component, and the moment you have this random component, B2 will not have a specific value, specific slope value, but rather it will assume a distribution according to the distribution that the error term assumes. So, that is why it is very important to understand that the regression coefficient is actually, it is a distribution, and it is actually the distribution, the properties of regression coefficient distribution is determined by the properties of the distribution of the error term. Okay. So, this is something that is very important for us to sort of keep in mind when we actually understand the error term, and that is why whenever we are considering any hypothesis testing or any other thing, we always get a distribution for the coefficient B2.